So let's talk about DSCP. DSCP is a 6-bit field inside of the IP header. So this applies to actually IPv4 and IPv6. And if we do our binary math there, 2 to the 6th power, that means we have 64 different values, which range from 0 to 63. So remember, the goal is to tag our packets with a value, one of these decimal values, 0 to 63, leveraging these 6 binary bits. And we're going to inform our devices what type of traffic it is based on the DSCP tag. So now I can take a traffic type, let's say again, voice over IP, and I can give it a tag. And this tag is technically arbitrary. I could give it a tag of 10. As long as my device, my router in this case, knows that a tag of 10 gets placed into, let's say, the low latency queue number whatever that is, in our policy, as long as the router knows this, then it's going to apply or be able to apply the packet into the correct queue. However, what is, do we want this to be completely arbitrary? I guess that's the question we need to ask. Because if I'm a network admin and I'm going around to different jobs, let's say I take a new job and I'm working on a new network, or maybe I'm a consultant and I'm going from network to network. Well, if it's a tag of 10 represents voice over IP at one location and a tag of 20 is used at a completely different location, and for that matter, if I'm a network admin working for one network and I'm applying a tag of 10 at a subset of sites and another network admin is applying a tag of 20, well, that starts to cause a lot of problems. And so what we want to do is to create a little bit of standardization, to create some standard values for specific purposes. And these standard values are known in DSCP as per hop behaviors. Again, to be clear, the routers don't care what values we use. They're just going to apply whatever policy that we define. This is for the sake of us humans. We want to be able to look at a value and know that that value usually means XYZ, whatever that is. So we don't just want to use an arbitrary value of 20 or an arbitrary value of 10. For example, we have a PHB, a per hop behavior of expedited forwarding, we call it, or EF. And EF is matched to DSCP 46. That feels a little arbitrary. There's actually reasons for why DSCP 46 was chosen, but either way, it's a fairly high value. And this typically is used for voice over IP. So DSCP 46, we could look at that and say, okay, well, again, that's great that we're all agreeing that DSCP 46 should match to voice over IP, but human readability becomes a slight problem because I might be able to memorize one value, but what if I have to memorize 12 different values? How do I keep track of them all? Well, rather than memorizing specific values, I can memorize a name. It's sort of like how we have IP addresses that map to URLs. It's a lot easier for me to remember google.com than it is for me to remember the IP address to google.com, even though the IP address is what really gets me there on the back end. So I can configure my router to say, hey, let's apply this policy to traffic marked with EF, and it knows on the back end that it's looking for a tag of 46. And of course, the router itself is not looking for 46, it's looking for binary bits of 101, 110. That would be the binary value of DSCP 46. So this is cool. We know that we've now got the ability to create lots of different per hop behaviors here. And so let's go ahead and talk about how these work. There's two other primary categories of per hop behaviors besides EF, which is sort of in a category of its own, by the way. So we have EF, and next we should learn about assured forwarding, or AF. So when we're looking at learning the different PHBs, we're typically focusing on EF as a standalone value and then a series of values within the assured forwarding category. There is one other category that we'll talk about, but it's not really used. It's a little more legacy. But, we'll still talk about it. Either way, we want to focus in on assured forwarding. This is going to give us 12 different classes, and usually this is enough. I mean, we've got one class over here with EF. We have 12 different assured forwarding classes. And if we need more than that, we might ask, okay, well, how many do we really need? I mean, yeah, we're given 64 different values that we can use, but how many traffic classes do we actually have in our network that we need to worry about assigning? Usually we have 6 or 7 or 8. That's typically what we see in our network. So having 13 classes available is usually plenty. Now, assured forwarding follows a specific format. The format is this. We say it's AF and then XY with 2 different values. X is the priority value or priority level, and it ranges from 1 to 4, and the higher the value, the higher the priority. So we want this to be high. The other value, Y, is our drop likelihood, or maybe we call it the dropability. Sure, we'll call it dropability. So how much can we, or how likely are we to drop this packet compared to other values or other packets that are in the same priority level? So we start with a priority level of, let's say, 1, but then we can have a dropability range from 1 to 3. And what's interesting here is the higher the value, it's the higher the drop rate. So we have to be a little bit careful here, because we might think that a value of 3 means it's a higher priority level and therefore it shouldn't be dropped as much. But we're actually saying that a 3 is likely to be dropped more than a 1. Whereas over here, again, the higher the priority level, the higher the, probably the treatment compared to other priority levels. We'll look at a few examples of this coming up. But the first thing we need to recognize is that there is a relationship between a DSCP value, again, that 0 to 63, and the AF XY value that we just talked about. This has to do with these 6 bits. And again, we don't want to drill too deep into this, but we're going to find that we have 6 bits, and we'll just say, let's just say something like 0, 1, 0, and 0, 1, 0. So when it comes to assured forwarding, X is going to say what these 3 bits are. Now I'm basically treating these bits like they're not there, so I'm just going to read this as 0, 1, 0. So this would mean X equals 2. Over here, Y is going to look at these 2 bits. So in this case, Y would equal 1, because I'm just looking at these 2 bits, treating all the other bits like they're not there. This last bit right here is always a 0. And that's why we're going to find that when we start breaking down assured forwarding values, that it's always a multiple of 2. Because in order for it not to be a multiple of 2, this bit right here would have to be a 1. So kind of interesting how this pans out. The Y value is independently a value that is multiplied by the 2's position, whereas the X value is an independent value, again, like we said, it's 2, except it's multiplied by the 8's position. So again, we've got the 1 and the 2 and the 4 and the 8's position, and then of course 16 and 32 and so on and so forth. Why do I bring that up? Well, because if I want to translate a value, let's say AF of, well, we'll just say XY again, what decimal value is that going to be? Well, I've got a really cool formula for this. I simply take my X value, multiply it by 8, so 8X, and then I add my Y value, which is multiplied by 2, plus 2Y. A little bit of algebra feels like maybe in here, but in the end, this is going to give us a really simple formula that tells us how to multiply this out. So, for example, if I were to say it's an AF41, we're going to take 8 times 4 plus 2 times 1. 4 here, 1 here, 1 here, and it fits into that formula. So that would be 32 plus 2. That is a decimal value of 34. a very simple way to calculate this. And if I wanted to work in reverse, like starting with 34, I'd just take out as many 8s as I could to start with, figure out how many 8s there are, and then whatever's left, divide by 2, and that tells me how many 2s there are. So it can work both ways. So that is how we can perform math calculations, but just be aware of that concept. So in the end, though, we have these 12 classes, and it's important for us to recognize this. So we've got, for example, AF4D1 through AF43. So what is this used for? Typically, we are going to be using AF40 whatever, 41, 42, 43, for our video traffic. So remember, voice over IP has its own category over here. We don't need to fit it into this. We usually put video traffic in here or otherwise high priority traffic. Always remember again that 43 is going to be more likely to be dropped than 41. So I've got 3 different classes within this priority level. And we're going to find that this applies to all of these. So AF, I'll just start saying 3x here. So 31, 32, 33. This is typically used for our critical traffic. And this is up to us as an organization to define. AF2x is going to be transactional. So sort of data transfers and whatnot. Although we also have AF1x, which is for bulk traffic. So really talking about backups and something that consumes lots of bandwidth and sends very large packet sizes. Now, at the end of all of this, we still have a DSCP value of 0, and this is typically used to represent our best effort, or really what we mean to say here is that it's all the rest of the traffic that's either unmarked or uncategorized. So really, I said 13 classes earlier, we technically have a 14th class here that we're likely to use in every single one of our networks. Now again, we're not likely to use all 12 of these, but they are available to us as much as we would like to use them. So I mentioned that there's a third category. This third category is known as class selector, which is abbreviated as CS. Class selector was created to allow us to migrate from IP precedence to DSCP. And class selector is fairly straightforward. We are simply going to only use the first 3 bits, which means whatever class selector we pick, it basically just represents X and it's multiplied by 8. What are we saying there? Well, if I have a CS of 1, this is mapping to a DSCP value of 8. I simply multiply 1 by 8. And then I can have CS of 2, which maps to 16, and so on and so forth. So we can go from CS0 all the way to CS7. And now the only way, or the only place primarily that we still see class selector in use is occasionally we will see it used down here as sort of a bottom of the barrel level of priority. And truly worse even than best effort, and we refer to this as scavenger class. This is typically marked as CS1, and what we are saying is kind of going back to that concept. Remember, we said best effort is not traffic we don't care about. We care greatly about our best effort traffic. It does need to go through. We cannot starve it. Scavenger traffic, on the other hand, if our network has traffic that fits into this category, is traffic that is very droppable. In fact, we would even say that it's starvable. Like, if we are having network congestion, then completely cut this traffic off. We do not want it on our network. So there are certain processes and things like that we might say, hey, that's traffic that would fit into the scavenger class. Again, all of the assignment of all these categories is going to be based on the organizational need. But generally speaking, what we've done, again, is we've created a bunch of standard values that we now have names for. We don't have to worry about the DSCP values. I don't have to define it that way, although as a network engineer, I might want to be able to translate it. But I don't have to worry too much about that. I can now look at a value like an AF33 or an AF13 or 12. I should be able to know what exactly that represents and how I can apply that into my network.
Thanks for watching. Be sure to click here to subscribe to CBT Nuggets and click the notification bell to make sure that you're aware of every time we post new content. If you're interested in a career in IT or you want to brush up on your IT skills, then swing over to our website, and while you're there, be sure to sign up for a free trial.